I'm going to talk about systems programming. My name is Andy Delcambre. I go by Delcambre on the internet. My last name is not phonetic at all, as you just saw. It rhymes with welcome. No one ever gets it right. I work at GitHub down in San Francisco. I'm pretty new there. I've only been there about 4 months almost, and I've been working on Gist pretty much since I started. Having a blast on it. We just relaunched right after I started, and it's been a lot of fun. So, similar to Jessica before, I kind of have the same background. Both my parents were in computing, and so I kind of came about this in an interesting direction. My mom's actually a computer science professor at Rutland State, and I swore up and down until I was about a senior in high school that I would never ever do what my parents did. I was going to rebel and do something like civil engineering instead. But then I tried it. I took a class in it when I was a senior, and I really, really liked it, and I ended up getting a computer science degree. So I tried to find my degree because I was going to put it up here because it's kind of relevant. I can't even find it. I don't know. It's somewhere in my apartment. No one's ever asked me for it. I don't believe that this got me sort of much in the way of jobs. No one's ever even asked me if I had a degree. So I don't believe that it's important to have a degree, but I also feel like there's pieces of my degree that I'm really happy that I have a sort of background knowledge. I'm going to talk about some of those pieces. So another little piece of history here. If you Google for Delcambre software on the internet, you don't find me, you don't find my mom. You actually find the company that my father and my grandfather started together back in the 70s called Delcambre Software. That my grandfather started taking night classes in the late 60s to learn how to automate his accounting software. And they made accounting software for small local governments in Louisiana for like 20 years, until the early 90s. So, needless to say, my grandfather did not have a CS degree. Again, I do not believe that a CS degree is required for being successful in computing. So, this is what I'm going to cover. These are the 2 classes at PSU that I took. Really not all of these, but little bits of both of these. And it's kind of intended to be just sort of backgrounds about all the stuff that we do every day, that all the pieces of code that power the things that we do every day, but not the stuff that we write every day. And I find it really cool, and it satisfies my curiosity a lot to know how all of these pieces work. Most of the code will run on pretty much any Unix operating system, but all the examples I'm going to show are kind of more specifically Linux-based. So you'll see a couple of command lines and a little bit of assembly and stuff like that. So that's all Linux-specific. The code that I will show runs on Mac too. I'll run it. So the title is Ruby Systems Programming. And what do I mean by systems programming? And it's basically writing any sort of system software on an operating system. This is stolen from Wikipedia, verbatim. But it says to operate and control the computer hardware and to provide a platform for application software. There's kind of 2 pieces there, right? You have the piece where you're interacting with the computer hardware, so this is like maybe networking, disks, things like that, I/O, screens, displays. And then you have this platform component where it's sort of like, it's not the end unto itself. It's the piece that you build on top of that goes underneath everything else. So I'm kind of going to start low, start about like how code executes on a computer. We'll work our way up the stack, and then at the end, we're going to talk a little bit about how an actual web server might be written in Ruby, like using the most bare bones components. So first, we're going to talk about how code actually gets executed on a computer. There's basically 2 modes that code can be executed on the CPU. It's actually implemented in the CPU, user mode and kernel mode. Basically, all the code that we write every day is run in user mode. Unless you're hacking on the kernel, you're not writing any code that runs in kernel mode. These are very different. They're actually implemented in the CPU. They have different permissions. They have different things that they can do. In user mode, there's basically only 2 sort of fundamental things that you can do without talking to the kernel. You can do what I call math. So actual math, string manipulation, floating point, security stuff, or like crypto stuff, anything like that you can do. And you can access memory, and you can only access the memory that you've been given access to by the kernel. So maybe things in the stack, the heap that you've been given access to, but you can rewrite that memory, but basically everything else. So all the things that are not on this line, right? You can't do I/O, you can't do networking, you can't write to the disk, you can't output to the screen, anything like that. You cannot do without talking to the kernel. So the code that runs in kernel mode, complete opposite. You can do anything, you can do everything. The kernel can read and write to any memory in the system, it can execute any instruction at any time. It can talk to any of the hardware, write to disk, manage the file system, it can write over the network, it can talk to the display drivers, it can everything. I mean, anything that you can think of you're doing, it can do. So you have these two modes, and all of your code runs in user mode, right? And let's say, for example, you were like writing a log and you need to write out to a log file. And so you need to write to a disk, which you can't do in user mode. So how do we do this? You might think that you're like writing the code, it's going along, and you switch modes. So you're like, okay, now I want to be in kernel mode. You write a couple of lines of code that maybe writes out to the file. You switch back to user mode, continue on your merry way. This is not how this works at all. All of the code you write, none of the code you write runs in kernel mode. It's all in user mode. The way this works is that in your program, you make calls via the system call API that execute in kernel mode. So again, going back to that log file example, you're chugging along, you say, okay, I want to write to a log file, you maybe open the file for reading, you make the API call in the kernel, you hand off execution, your code is no longer running, the kernel mode runs, the kernel code runs, it opens the file, it does all the things that are necessary on the file system, and then it hands you back a pointer, and then your code continues on. You can make another API call, hand off that pointer, and say you want to write something to it, and then the kernel will again do that, the necessary stuff to make that happen. We had to exist. So I was kind of curious how many syscalls that we sort of make every day in Ruby. I didn't actually know the answer to this. I tried this out. Estrace is how you can see what system calls a particular program is running. This is on Linux. There's another one called dtrus. It uses the dtrace API on Mac. So you run this, you hit the PID, it just prints out one line for every system call that gets made. So I booted up the gist app locally, got it primed, I hit it with a request, and then recorded all the API calls that were happening with that request. You can see this go by. It's kind of a lot. It takes a few seconds. But it's doing a lot of stuff. You can see some stuff on there. Here, but closing a file, somewhere in there there's an accept. Talk about that later. Some get peep, parent process ID stuff, some changing process masks, all kinds of stuff. So this actually updates significantly faster than the frame rate of this video. Across that entire request, that output there, 120,602 system calls for one request. So some people might say that this is the result of Ruby being inefficient with system calls, which is probably true. This is running in dev mode. It would probably be lower in production. But I still think it's an interesting example. And really, it's doing a lot of stuff that needs to talk to the kernel. You're connecting to MySQL, Memcache, Redis, you're reading and writing over the network, you're probably writing out to log files, you're reading templates off disk, that doesn't even include any of the web server stuff, where you're listening for connections, accepting connections, reading off the network, writing back to the network. So you have all of these pieces that are actually doing system calls. And so it kind of makes sense. There's a bunch of other stuff that's doing, of course. So you might think that with all of these system calls and the fact that you can't really do anything without making system calls, that this API would be a really big API. It would be hard to understand and hard to learn. There's 326 system calls, period. This is out of Linux, on the kernel. This is off master as of a couple days ago. There's 326, period. You cannot make any system calls that are not in the stable. Little aside, this is how you actually make a system call. So this is the move system call. Basically, those EAX, EBX, and ECX are registers. EAX is where you always put the ID of the system call you're making. And then that last line is an interrupt. Interrupt 80 in hex is the syscall interrupt. So basically, that's how you hand off execution to the kernel. That says, okay, I'm done, you take over. So the interesting part of that is that that number, there can't be any blank spaces in that table. It's not like there's a map which says like open is number 5. It's just a list. And so you can't have blank spaces in that syscall table. So of those 326 system calls that we had, 65 of them are the sys and syscall implementation. The NI stands for not implemented. These ones are all the ones that are like historical, have been deprecated, aren't used anymore, but you can't have blank spots in the syscall table. So you're only left with like 260 actual calls that actually do anything at all. It's a pretty small API. It's pretty impressive that it's lasted as long as it has. So we're kind of switching gears here. So we're talking about system calls and sort of the operating system level stuff. Now let's talk a little bit more specifically about how we do web programming, and like how we write a web server in Unix. We're not going to be able to cover all 260 and actually do stuff. We're kind of going to limit it down to just the ones that deal with receiving connections from the web. So first, a little bit of history. I think this is kind of interesting with how the APIs that we use today have been developed. So back in the 1960s, there was an operating system called Multics. This was a research operating system developed by MIT and AT&T Bell Labs, as well as a few others. Ken Thompson and Dennis Ritchie worked on this at Bell Labs. The program, it was successful, and it was a research operating system, so it developed a bunch of new concepts, but it wasn't really used for anything real. And it had a lot of problems. It was kind of too ambitious for its time. So some of the people on the Multics team worked at Bell Labs, and then at Bell Labs they developed what they called Unix, which was intended to be sort of a reduced problem set of Multics. It was intended to be originally single user as opposed to multi-user, which is how they came up with the name, Multics to Unix. They eventually developed multi-user support, so they renamed it, kind of rebranded, and dropped the CS and switched to UNIX. That was in 1970. So at that time, AT&T was under restrictions due to the antitrust settlements in the 1950s. So AT&T was not permitted to sell the operating system without giving a license out for free to anyone basically who asked. So a bunch of universities, including Berkeley, UC Berkeley, got licenses for the source code and had source code. And so that's where a lot of the sort of development of Unix happened thereafter. In the late 1970s, 1978, the first ESD was released. This was Bill Joy's project, largely, at Berkeley. He basically he and a team took the source code from the AT&T Bell Labs Unix, kind of packaged it up, brought it all together, and then added a few programs to it. He's famous for two programs that he added to it. One was C Shell, one of the first actual shells that nobody uses anymore, for better or for worse. And the other one is VI, which you may have heard of. So that was where that came from. So over the next 5 years, ESD released a few more versions. They ported it to a couple of different hardware. This was back in the days when you had to kind of change things to get them to run on each new computer. And in 1983, which is also the year I was born, ESD 4.2 came out. And this was the first version of a TCP IP stack that was like widespread use. TCP IP was actually in RPC like a little bit earlier than this, but it wasn't really primarily used until around now, and a little bit later. So what's interesting is that the API that was developed in 1983, 30 years ago, is the same one we use today. We still use ESD sockets, and it's one of the few parts of Unix that has been ported to almost every operating system. It's basically the only way we interact with networking today. There's a few other ones that don't get used very often, but even on Windows, they're still using that same the same API, not the code, but the API. So that code, or that API, is called ESD sockets. It's a really simple API, and it's kind of, I imagine that's why it's lasted as long as it has, but it's pretty amazing that we're still using really the technology from 40 or even 50 years ago, and we're using the API from 30 years ago, pretty much unchanged. So this is the kind of server parts of the ESD sockets API. There's another probably 4 or 5 that are kind of used for client stuff and like DNS lookups. This is the stuff I'm going to talk about. We're going to write a web server. Go through each of them in turn. So the first one there, everything in the ESD sockets API is basically dealing with sockets. It's the most fundamental unit. So the socket API, the socket method, calls or creates a socket for you to interact with. You basically tell it what kind of socket you want, you get that back, and all the other ones deal with that socket. The second function there is bind. So this binds that socket to a specific port on your computer and an interface. If you're on a server, you might have multiple interfaces, so it tells you which one to listen on, and you bind what port you're going to listen on. Third one there is listen. Listen tells that socket to turn into passive mode where it can receive incoming connections. And you accept those incoming connections off the socket. So every time somebody connects, the accept will return a new socket which is connected to that client. Once you have that client socket, you can send and receive across it, and then at the end you close the socket. This is largely dealing with TCP sockets, not UDP, because we're dealing with a web server, right, which is TCP. So a little bit of overview about how TCP works. This is a very common diagram for how you show packet flows. The client's on the left there, the server's on the right, and time flows from top to bottom. And I don't know if you can see the arrowheads, but basically everything's going downhill. And each one of those lines is a packet that goes across the network. So there's basically 3 parts to a TCP connection. First, we have what we call the 3-way handshake. This sets up a TCP connection. So the client first sends a send packet, so for synchronize. This is kind of setting up some of the internals to TCP. The server receives that, and it needs to acknowledge the packet. Every single packet in TCP is always acknowledged. That way the protocol can retransmit if it doesn't, if it didn't get the acknowledgement. So the server responds with the acknowledgement and its own send packet to synchronize from that direction. TCP is bidirectional. You can do those both in the same packet. And then the client acknowledges that send packet. Once those three things have happened, now we have a bidirectional communication setup, streaming communication. So at the API level, you're no longer dealing with packets at this point. You're just dealing with streams. TCP and the underlying architecture handles all of the low-level, like sending packets across the network. So once those three packets have happened, the connection is what's called established. And from here on out, basically, you're just dealing with sending data back and forth across the line. So if this is a really small connection, maybe it's just like a tiny web request, there might actually only be 3 packets transmitted. If it's like a long-running SSH session, or like you're doing merge sync across the network, sending lots of data, this could be many packets. But in general, it all looks the same. So the client's going to send some data. Maybe this is a web request. That could be like an HTTP request. The server, again, needs to acknowledge that packet. So it sends the ACK. And again, you can put both an acknowledgement and data in that packet. So it will respond with the web response, potentially. This might only be one packet. Our maximum packet size in TCP is like 1,500 bytes. So like a small HTML page, easily fit in that. And then the client, again, needs to acknowledge that data packet that was sent to the server. This could be much longer, again. If one side, if like the server was responding with a really big file and sending lots of packets, the client would still need to acknowledge every single one of those. There's tricky things you can do where you can kind of buffer those and then send one packet every few packets, so you don't have to constantly just be flooding back acknowledgement packets. But in general, there's one packet that goes back the other direction, even if all the data is going in one direction. So finally, all of these packets are done transmitting data. You need to shut down the connection. You do what's called the four-way handshake. So because this is bidirectional, each side can be shut down in turn. You don't have to shut down the entire connection at the same time. So in this point, let's say that the server is done sending data to the client. It sends a then packet to finalize the connection. The client acknowledges that. And then at some point later, often this happens immediately, but at some point later, the client then sends its then packet. The server responds with the acknowledgement. At this point, the connection is closed. No more data can go across the connection. So you can kind of see this. This is a command in Linux and Unix. This runs on Mac. You can see this LSOF is listed open file descriptors, and all these things are file descriptors, even in connections. So this is a sample. This is actually the code that I'll show in a minute running. This is a program listening on port 80, and then a client that's connected on port 80 that's currently transmitting data right now. So you can see the socket itself is in the listen state. This is ready to receive incoming connections, and then that client connected. It did the three-way handshake. Now it's in the process of transmitting data, so that connection is established. You can't really see them in close; they kind of disappear pretty fast, but you get the idea. And sometimes, like if you look at this on like a web server, maybe Nginx is there, you'll see lots of established connections because they can handle multiple connections at the same time. So this is kind of like we're still working our way up the stack now. Talked a little bit about the kernel, a little bit about syscalls, a little bit about TCP, and now let's move on to HTTP. So this is probably moving into familiar territory. We've all seen this before, but this is the actual text that gets transmitted across the network. So in an HTTP request, that first line is kind of the most important line. It sends the method that gets called. So in this case, it's a get. The second parameter there is the path that you're going. This is what will be in the URI in the command or in the URL bar. And then the version of HTTP, which is almost always 1.1, but it gets sent every time. Then you have some request headers. It says the user agent, curl, the host, Google, and it's accepting any sort of content type back. If you were doing this in a browser, this was just an example I did with curl against Google. If you're doing this in a browser, that accept would actually have some more specific stuff in it, and the user agent would be different, but it's the same stuff. If you were posting and you sent a response body or a request body, like maybe a form upload, there's going to be a blank line after the accept, and then all the post body data is just right there. So on the other side, after the request happens, we get the response. Looks very similar. We have the first line again, which is the header for the response. Again, the version, still 1.1, and then we have the status code that comes back. In this case, this is a 200 OK. This was a successful connection. It's always both the status code number and then the text version of the status code. So this is 200 OK, 404 not found, 302 found, 304 not modified, et cetera, right? But it's always got both. Then you have some response headers. It has the date, some caching information. It says we're getting back HTML content, what server we were hitting, some sort of Google web server, and some transfer encoding stuff. Again, a blank line, that's just one blank line that looks a little spaced apart, and then all the data. This would just be the HTML that comes back in this case, truncated for brevity. So we're kind of at the point now, let's look at some code. So there was I'm going to show some code on the next slide. Don't try and read it. I'm going to go through it line by line, literally every single line. This is not production code. This is like, don't use it in production. It's an example. This is huge security vulnerabilities. You can access any file in the file system. But it's cool because we're using the lowest level possible APIs in the system to be able to write an HTTP server. The cool thing is that it's only 20 lines. This is the entire HTTP server this rolls on. I'll show this in a minute. So first, we require the socket library. This is just in the standard library. It's the most sort of baseline fundamental networking API that exists in Ruby. We define some constants for later just to save some lines down there. And then we get into the meat of the program. So first, we create a new socket. This is equivalent to the socket method in the API, in the ESD Sockets API. We're giving it 2 parameters there. This basically tells it what type of socket to open. The first parameter is this inet. That is the sort of layer 3 level. So whether we're talking about IPv6, IPv4, USD, or Unix domain sockets, and then a few other ones that are much less commonly used. In this case, we're just going to do IPv4, sort of your normal 32-bit addressing 8.8.8.8 or whatever. And then the second one is saying that we're going to be doing TCP. This is the layer 4 level. So in stream means that we're doing TCP. We're going to have a bidirectional streaming API. If this was said datagram, then we'd be doing UDP. And again, there's a few more options, but those are kind of the most common. You can also get a raw socket that basically just lets you do whatever you want. It doesn't do anything as far as like writing or helping you out. You're just talking right on top of the IP layer. The next line down, it's actually 2 lines together. That first line there is it's a helper method in Ruby to create the correct structure that the low-level API can handle. But it says that we're going to listen to localhost 127.0.0.1 on port 11.080, just some random high port that I chose. So that doesn't actually make an API call. That's all done in Ruby. Then we take that structure that we just created, pass it to bind. That socket is now bound to port 11.080 on localhost. Next, we call the listen method on the socket. This turns that socket into a passive socket, so it's ready for incoming connections. And at this point, like if we had a sleep here or something like that before we started accepting connections, if anybody connected in that point, that client would be queued and wait for us to accept that connection. That 5 parameter that we pass to it is how deep that queue is. So up to five clients can connect. They'll be held in queue until we're ready to process them. The 6th one connects, it'll be dropped. So now, this is kind of done with the setup. The socket is ready for us to accept connections. So now, this blocks and waits for the client to connect, and then creates a new client socket for that connection that we can then read and write over to talk to that socket. In the Ruby API, this returns a tuple. We only care about the first parameter, which is the actual socket. That's why I have 0 there. First parameter for the first part of the array. This is my 100% standards compliant high performance HTTP parser. If you remember, this is what the first line of an HTTP request looks like. So I'm just pulling the first kilobyte off the network because I don't know how long this might be. And we're taking and splitting it on spaces. So we have the method, a space, a path, a space, and a bunch of stuff we don't care about. We take the second one, which is the path, and we move on. We take the path that we got, we expand path it against the current directory, so we can get anything off the current directory. Most browsers won't let you put ... into the command line or into the URI. Curl doesn't care. This will let you pull off Etsy password if you want. Don't use this. We check to see if it's actually a file and that it actually exists on the file system. If it does, we're going to respond with that file directly over the wire. So we're going to read the contents off disk. We're going to send the 200 OK. We're going to send the content link. This is kind of just to show that we send headers, how you send headers, what they look like. The browsers really don't care. You don't actually need to send any headers at all. Curl was not happy if you didn't send the content link. They complained, but the browser worked fine. And then we just send the contents, and we have those two new lines. We have a blank space to separate the headers from the actual contents of the file. If, on the other hand, that file does not exist in the file system, we simply send a not found, which is defined at that. So we send for not found, again, the content link, and then the literal string for not found. And finally, we close the socket. This triggers that four-way handshake to close the TCP connection, so that way the browser's not just sitting there waiting for more data. So that's the whole thing. It's a full web server. Right? Let's see it run. So just to prove, it's the same file. Looks basically the same. No trickiness, no extra libraries. There's a file called foo. I'll show you. Oh, right. So we have a file in the current directory, has blah, blah, blah on it, it works. The highlighting is just because I have a plugin in Chrome. We can get the program itself. And if we get something that's not there, we get not found. So it's a real web server. It's actually server bound. So even though this is cool and I like it and it's fun, why do we care? Like, I expect that somebody will probably write another HTTP web server, HTTP parser in Ruby before, I don't know, the year is out. Who knows? We'd like to reinvent stuff around here. But I think this is really cool to just kind of know the fundamentals about how the pieces of code that we actually use work. So I looked inside of Unicorn, and I found code that is basically exactly like the code I just showed. It's buried down in there, and there's a lot of code wrapped around it. There's a couple of lines here that might look familiar. This is the IPv6 code as opposed to the IPv4 code because the IPv4 code is written in C, not in Ruby. My theory on this is that nobody uses IPv6, so nobody cares. But who knows? I don't know. But you can see we're still creating the same, we're using the same exact API. So we're using the raw socket API here. We're using a slightly different version that uses constants rather than symbols. I made it shorter using symbols. But we're calling it AFINET6 there, which says to use IPv6. And then we are passing the streaming protocol again to say with the TCP. We have a couple of options that get set. We bind using the same API as before. So we're doing that same socket in with the port and the address. This is actually an alias. These two numbers are the same. The pack socket in and the socket in I was using. Again, I was using the shorter ones to fit on the slide. And then in the code that I showed, we were using accept to wait for incoming client connections, and in Unicorn, we use select. So accept only accepts on one connection, but Unicorn can listen on multiple interfaces at the same time. So select basically, at the very most fundamental level, can look at a bunch of different sockets that are currently accessible, and the first one that responds, you get back the data from. So this is basically inside the Unicorn workers. This is the line of code that actually runs. That L is an array of sockets that can be connected, or file descriptors, pretty much anything. And this is how it actually runs. So I think this is really cool. I find this fascinating to play with this stuff. I'm not really probably going to write a web server tomorrow, but it's fun to look at. I find it satisfies my curiosity to kind of dive down and know how this stuff works. And I find it probably makes me a better programmer in Ruby, even at the high levels. So that's it. Thanks a lot.